Hello and welcome to this clip going through the 2016 Unified Chemistry Practice Paper. It's the version from the OCR website's Open Access Assessment Materials section. It doesn't constitute a mark scheme. It hasn't been endorsed by OCR. Please can you treat it only as a guide and my own personal interpretations as a teacher of the questions and how I might go about dealing with them. If you take it in those terms, please use it as you wish. Like I say, the paper itself is freely available from the OCR website, so please visit the OCR's website to access the paper itself plus the mark scheme. This is just some guidance I would suggest if you were doing this paper. Okay, so it starts off by asking you to give chemical explanations for some common statements, some more everyday than others. So what I'll do is I'll take you through each of them and just go through what I think you need to be recalling as you go. So the first one says bromine has a higher boiling point than chlorine. And whenever I see boiling point, or whenever I see a sentence comparing boiling point, I automatically think intermolecular forces. So here's what I'd put for this one. So even though the mark scheme just says stronger, more London forces than chlorine, I'd also put in more energy needed to overcome them, so you give a reason to support your statement. So the next question, a carton of milk expands on freezing. So bearing in mind that milk is mostly water, it's the intermolecular forces in the water that you need to be thinking about. So if it expands on freezing, so thinking back to the first year when we talked about anomalous properties of water, one of the things we covered was the fact that it forms an open lattice when it freezes into ice. So the water in the milk forms ice, and the hydrogen bonds in the ice form an open lattice, which means the H2O molecules are held apart, which means it takes up more space, so the carton of milk will expand. The next one says potassium is placed immediately after argon in the periodic table. And the reason for that would be that potassium atoms have one more proton than argon atoms. So moving the page down now so you can see what the next question is asking. The reaction of ethane with chlorine under UV radiation is a poor method for preparing a high yield of chloroethane. Now here the key part of the sentence is actually the clue that tells you what to write. So ethane with chlorine is going to be an alkane reacting with a halogen under UV radiation, so think free radical substitution. So the obvious reason would be that further or multiple substitutions would occur. The word chloroethane, which I'm just about to underline, actually implies that the desired product that you're trying to make is monosubstituted. It doesn't say dichloro or trichloroethane, it just says chloroethane. So there's nothing much you can do to stop or prevent further multiple substitutions occurring. So that's the reason it's a poor method for preparing a high yield of that particular compound. So moving the page down a bit to the next one. It says water has a concentration of approximately 56 moles per decimeter to the minus 3. So to think about what they mean by this, what it requires you to remember is that the fact that 1 gram of water is the same as 1 centimeter cubed of water under standard conditions. So therefore what you have to do is think how many grams of water in 1 mole. And then make the connection that 18 centimeters cubed of water is going to be 1 mole. So therefore, how many times does 18 centimeters cubed go into a decimeter cubed? And by converting a decimeter cubed into 1000 centimeters cubed, you can easily work out that it goes in approximately 56 times. Okay, so the final one is asking you about carbon-carbon bonds and benzene, so it's switching over to aromatic chemistry. And the key piece of information, or the key statement they want to explain, is all the same length. Why are the carbon-carbon bonds all the same length? And hopefully you've spotted that the statement is actually one of the pieces of information you're expected to go away and learn to disprove the Kekulé model. And the new model of benzene after the Kekulé model is the idea of the pi bonds being delocalized all the way through the ring, all the way around the ring, which creates the delocalized pi system. So that's what you need to put in there to explain what's going on. Okay, so let's go to the next page. More statements. So this time, infrared spectroscopy distinguishes ketones from carboxylic acids. So you need to think about the two functional groups. It might help at this point to actually sketch them in. And if you do so, you can easily see that one particular bond within the carboxylic acid functional group is not in the ketone group. So they have the C double bond O in common, but they don't have the OH in common. So in terms of the IR spectroscopy, you go to your data sheet and just state what the actual absorption is. So the next one, it says 1.323 grams of N2O gas has a volume of 1 decimeter cubed at 100 kilopascals and 400 Kelvin. So the first thing you need to be thinking here is, do I have enough data, because I'm talking about a gas, for PV equals nRT? And we do. We have volume, we have pressure, we have temperature. So what you've got to do is to clarify the fact that 1.323 grams of nitrogen, dinitrogen oxide has that particular volume. You need to work out the number of moles of dinitrogen oxide. So you can use a rearranged version of PV equals nRT, and don't forget, of course, that you're given the volume in decimeters cubed and you need to convert it to meters cubed, which I've done in my calculation. So now that gives us 0.0301 moles. But we still haven't quite connected it with 1.323 grams. That's where moles equals mass over mR, or more specifically, mass equals moles times mR comes in. So by multiplying 0.0301 times 44, which is your mR for N2O, that gives you 1.323 grams, which proves the statement. Another calculation this time, 4.25 grams of C6H5COOCH3 contains 1.88 times 10 to the 22 molecules. So whenever I see a number of molecules being quoted, I think Avogadro's number. So therefore what we need to do here is work out the number of moles times Avogadro's number. So what I've got to do is work out the number of moles of C6H5COOCH3. So the MR of my C6H5COOCH3 is 136 grams per mole. So dividing 4.25 over 1.36, or should I say 4.25 over 136, beg your pardon, that gives me 1.884375 times 10 to the power of 22, which proves this statement as well. So moving the page down a little bit further, where it says the rate of hydrolysis of one bromobutane is faster than that of one chlorobutane. So immediately what you should be thinking here is the relative size or magnitude of the carbon-halogen bond enthalpies, because it's the carbon-halogen bonds that need to be broken before the hydrolysis of the haloalkane can take place. So to cover my bases, I've also made reference to the relative strength of the bond, which is inextricably tied, obviously, to the bond enthalpy. So I've mentioned bond enthalpy and strength just to cover myself there, just in case. So let's move the page down, and it doesn't look like there's anything more. Nope. So, next page. I'll move the page up here because it looks like it's going to be a long answer question. I can tell that because it's got a star next to it. So if you have a banded question, that means it's automatically 6 marks. So the answer should be chemically correct and clearly explained, because the level that will initially be awarded by the marker comes from the clarity of your answer. The marks within the level are then decided on from the correct level of detail within that level. So before I go any further, I highlight what the instructors are telling me to do. They want me to plan a series of tests, and they must have a positive result for each ion. So that means you can't say it must be sulfate, for example, because there wasn't a precipitate with barium chloride. You must say something like it was a sulfate because it did form a white precipitate when added to barium chloride, and that the precipitate would have been barium sulfate. It also says for each test include details of reagents, observations and equations. That's 3 different things that they want. They also want you to explain how your observations allow the ions to be identified. It also allows you to include a flowchart or a table in your answer if you wish. So let's take their advice. Let's think about a table that you could actually produce. So it's important also to include the order in which the test should be done. So why don't you pause it for a second and have a think about it. I would suggest maybe doing one set of tests for the cations and one set of tests for the anions. But then I'll leave you to have a think about it. So do pause the clip, try it out, and then see if we agree. So that might be a table that could represent the tests for the cations. An inference is obviously a conclusion you can make, so the species that's responsible for the observation is what I've written in the inference column. And obviously you need the equations as well, and I would advise you to stick to ionic equations because it's a bit easier just to write out what's happening rather than trying to balance a full equation. It saves time. So you can add in the equations like that, and what we can do now is just put a couple of sentences to explain the rationale behind what we did. So that covers us for the cations. Now we have to do the anions. We need to move the page down a little bit to do this. Now obviously on the actual paper there's more room on the next page. So I've copied the next page over so you can see at the bottom of the screen the fact that it's the 6-mark question. So now we can do the anions. So those are the kind of things you'd put for your anions. You'd add nitric acid and add barium nitrate, not hydrochloric acid or barium chloride, because that would interfere with the chloride test. And you'd also do it in that order. So do carbonate first, then sulfate, then chloride. So 2 tables like that, with a couple of sentences to explain the logic in each one, would probably cover you. So I would recommend using the table approach rather than writing lots and lots of text, because otherwise you'd get yourself in a terrible muddle and you may end up spending 3 or 4 minutes making one point in amongst quite a lot of confusion. I'm not being mean by saying this, but it's what I've seen time and time again when I've marked these kind of papers and these kind of questions. When you've got a lot you need to put down, it's really important to make sure that you put it down in an organised way. It's a little bit, I suppose, like NMR tables, the NMR analysis table, where you put the chemical shift, the environment it's from, etc., etc. So when you've got a lot of information you're trying to put down, do consider using a table to help yourself organise your thoughts. It's just a bit of advice. Okay, so let's go on to the next part of the question. And you can see clearly there's some more space here. You'd be advised to use that space in the exam, obviously. I didn't, because the nature of the app I'm using to produce this clip means that it's difficult to go back and forth between screens once you've actually recorded a screen. So a bit of a lame technical reason, but unfortunately it meant I had to get it all out of the way on one screen. So what that means, I'm going to move this up, and we're going to have a look at the next part of the question. So that was only part A. Part B is the dissociation of water is measured by the ionic product of water. And the first thing to do here is to pause and just make note of the fact that the KW from the data sheet, you don't actually have to physically write it in, but you'll have your data sheet in front of you when you're taking the paper. The KW from the data sheet is 1.00 times 10 to the minus 14 moles to the power of 2 decimeter to the power of minus 6 at 298 K. And if you look at the actual question, it says that KW varies with temperature as shown. So it asks you to calculate the pH of water at body temperature 37 degrees, so we need to extrapolate from the graph. Let's find 37 degrees. So that gives us roughly 2.3 times 10 to the minus 14 by extrapolating using the graph. So what we do now is to calculate the pH. So just remembering that H plus and OH minus are equimolar in the dissociation of water, that means that Kw equals H plus. So now we need to work out the pH from that. So we can work out that the H plus concentration is 1.52 times 10 to the minus 7. I should technically call it moles per decimeter to the minus 3. So doing the minus log of that gives you 6.81 as your answer. So always a good idea, instead of burying your answer somewhere in your workings like I did, to actually just repeat it and put it in the answer space. Otherwise the examiner might miss it. So it's just good exam technique there. So let's now go on to the next page. So this first part should be fairly straightforward. It's an empirical formula calculation straight out of your first year. So the first thing to do is obviously the percentages over the relative atomic mass of each element, straight off the periodic table, no rounding up, no rounding down. So once you've got your rough ratio, you then divide it by the smallest, which in this case is 0.373. So now that enables you to put in the empirical formula. So the next part says the formula of this cobalt complex can be expressed in the form COLMX plus Cl minus N. So it doesn't tell you what L means. It obviously means some kind of complex ion. So to work out what it might be, so looking at the fact that the cobalt and the chlorine have already been used up, that must mean that the L must be a species of some type containing nitrogen and hydrogen only. So that now allows us to put in that number, or at least that worked formula. It's not the final answer, it's only a working. So what can we take from this? Well, mathematically, when they write something like this in algebraic form, if there's different letters, that means that they're actually different numbers. So what we need to do is look at the ratio of nitrogen to hydrogen. So we know from the empirical formula that it's 6 to 18. So in simplest form, that's going to be 1 to 3. And seeing as we're dealing with cobalt, which is a D-block element, or more importantly, transition metal, L could be an NH3 ligand, an ammonium ligand, ammonium ligand, I should say, sorry. So now we can start to put together a possible formula. So because we know that the maximum number of NH3 ligands that can fit around a cobalt central metal ion is 6, that must mean it's CONH3 6. Where did the 3 plus come from? So 3 times Cl minus. So where does that leave us with what I said earlier about X, M and N are different numbers? I'm going to slightly change that into could be different numbers. So in this case, it doesn't necessarily mean that they are, it means that they could have been. So going back over this calculation, that's quite a difficult mark to get, that's quite a demanding one. I would say that would be definitely one of the few marks where it tests out the A and A star type candidates. But if you take a little bit of common sense from your empirical formula and from the fact that you've got nitrogen and hydrogen that haven't been used up, at this point that must mean you're well on your way to working out that it's NH3, and from there you can work out the formula. So going on to question 3, it tells you that it looks at properties of iron compounds and iron ions in different oxidation states. Now, I'm not being obvious by writing that at the top of the screen, but what I'm trying to do every now and then is just to remind you what the question is actually trying to help you with. So it's telling you to think about transition metals, specifically iron. So it starts you off by asking you to write the electron configuration for the iron 2 plus ion. So it's the same as the iron atom minus 2 electrons. Now what you've got to think about is where those 2 electrons are going to come from, which subshell. And not forgetting that the 4s orbital, or 4s subshell if you want to call it that, empties first. That's where the 2 electrons are going to come from. So I write out the electron configuration as if I'm doing an atom, but I remember that I'm losing 2 electrons because it's becoming an Fe2+ ion, so therefore I remove 4s from my electron configuration. So then it says, how many orbitals contain an unpaired electron in an ion of Fe2+? So the unpaired electrons are only going to be present in the 3D subshell, because the 1s, 2s, 2p, 3s and 3p subshells are all full. Now remembering it's 3d6, that must mean that one of the 5 orbitals in the 3D subshell is full. So therefore that leaves 4. Then it moves on to talking about FeH2O6 3+. And it says an excess of aqueous potassium cyanide is added to an aqueous solution containing FeH2O6 3+ ions. A ligand substitution reaction takes place, forming a complex ion that has a molar mass of 211.8 grams per mole. So remembering that the cyanide ion acts as a ligand too, it's quite simple really to put it in, isn't it? So we can write it in like that, and just to double check that it is actually 6 cyanide ions that swap for 6 water ligands, we can work out the MR of our FeCN6 3-, which gives us 211.8 grams per mole, so it shows that we're in the right place. Okay, next part of the question. It talks about the complex ion FeH2O6 3+, behaves as a weak Bronsted-Lowry acid, and it shows how it dissociates to release an H+ ion. And it asks you to write the expression for the acid dissociation constant for that particular ion, for FeH2O6 3+. Remembering that the general Ka expression is what's in blue, the specific one you want is this. So not forgetting, of course, that because you're dealing with ions in solution and hexa-aqua ions, or complex ions I should say, you have double square brackets. One square bracket for the fact it's a concentration term, and one square bracket for the fact that it's a complex ion. So the next part of the question asks us to calculate the pH of a 0.1 moles per decimeter to the -3 solution of FeH2O6 3+ to 2 decimal places. And as that's a specific instruction, it's important it's followed. So first of all, you can calculate the hydrogen ion concentration using the usual method and substituting in the values from your Ka expression. Then you have to work out the pH. And again, putting the answer in the actual answer space, we have 1.61. Let's move the page down a bit, see if there's anything more at the bottom. No, we're at the bottom, so let's go to the next. So part D, it says Fe2O3 can be oxidized by ClO- ions under alkaline conditions in a redox reaction. And it says unbalanced half equations for this reaction are shown below, and it wants you to balance them and construct an overall equation for the reaction. So the first thing to do is to assign oxidation numbers. So you can see quite clearly now that it's only the chlorine that changes oxidation state, and it's reduced from +1 to -1. So if it's reduced, that must mean that it has 2 electrons that it's gained. Or more specifically, if it's reduced by 2 numbers from +1 to -1, so its oxidation state has dropped by 2, it must mean it's gained 2 electrons. So the next thing to do is a similar kind of process, but on the other half equation. So starting with the Fe2O3, you can see that going back to step 1, you've got a total contribution to the oxidation state of 0 of the whole compound of -6 from oxygen. That must mean that each oxygen atom actually has -2. So that must mean that if there's 2 Fe's, each Fe must be +3. So now going over to the FeO4 2-, 4 lots of -2 makes -8, so for the whole thing to be 2- overall, the iron must be +6. Now what must have happened there is for that to be achieved, 3 electrons would have had to have been lost. you've got to be a little bit careful here, because if you look carefully you'll see that it's Fe2O3 going to FeO4 2-. So you've got to balance the species first, so that 3 needs to be removed for now. So what must have happened is Fe is oxidized from +3 to +6 twice. So there's 2 Fe's in Fe2O3. So that must mean, in actual fact, 6 electrons are lost. So now what we've got to do is balance out the OH minuses. So we have 3 oxygens in Fe2O3 and 1 oxygen in OH minus. So far so good. We have 8 lots of oxygen, don't we, in FeO4. So let's just work this out at the bottom. So on the face of it, it looks like because of H2O, you'd need 2 OH minuses. But finally what you've got to do is balance the charges. So bearing in mind that on the right hand side you actually have 10 minus, that means on the left hand side you've got to have 10 minus. Which means we now need 10 OH minuses and 5 H2Os. So now finally what we can do is we can multiply each half equation to balance the electrons. So the overall that we'd want as a result of that, we're not quite finished yet, because if you look at it closely you can actually cancel out some OH minuses and some H2Os. Like that. So now we can put the final answer in. Okay, so let's go to the next question. So this is I looked at things as a graphical rates type question. It says methanoic acid and bromine react as an equation, and the student investigates the rate of that reaction by monitoring the concentration of bromine over time. So the way that sentence reads to me is it's going to be about half-life. So the student uses a large excess of HCOOH to ensure that the order with respect to that will be effectively 0. So that means the rate might change, but the change in the concentration of methanoic acid is going to be negligible, so effectively it's unchanged. So from the experimental results the student plots the graph below, so let's bring the complete graph down. And I'm going to have to make the graph a little bit smaller, I think, so you can understand the question fully. So the first thing it asks you to do is to suggest how the concentration of bromine could be monitored. So bromine is obviously coloured, so you could measure how much the colour fades. So I'm actually looking ahead a little bit on the paper. If you've got a copy of it, you'll see what I mean. And the next screen is going to be about using the graph, so I'm going to make a copy of the graph and move the graph over onto the next screen. So the next thing says, suggest a different experimental method that would allow the rate of this reaction to be followed over time. And you may remember that there was CO2 produced. So therefore, you could measure the rate of CO2 produced, or measure the volume of CO2 produced. And then it asks you, why would the use of excess HCOOH ensure that the order with respect to it is effectively 0? And like we said before, it's because the concentration would be relatively constant. And the next part says using the graph. So I'm just going to bring that part of the page down. And I'm going to bring in the copy of the graph that I made from a few seconds ago. So there's two things you've got to do here, because it's a levelled question. You can see it's got a star next to it. So the mathematics are going to involve taking a tangent at t equals 0 and working out the gradient. Then you need to get the rate constant by using t half for the half-life to determine the order with respect to concentration of bromine. So by drawing a tangent and working out the gradient using dy over dx, that gives us a rate of 4.3 times 10 to the minus 5 moles per decimeter to the minus 3 second to the minus 1. So looking at the equation, you can see that the rate is K times Br2, concentration. You ignore HCOOH because it tells you to. So mathematically it gives us 4.3 times 10 to the minus 3, because we're dividing 4.3 times 10 to the minus 5 by effectively 0.05. 0.01. But we need to work out the units, so we can do that as well. Okay, now I made a bit of an assumption, didn't I? Because it says the large excess of HCOH means that that will be effectively 0. The order with respect to HCOH will be effectively 0. It does say earlier on to use the graph, and what I haven't done yet is work out the half-life. So I need to do 2 half-lives to make sure they're constant. So to get my last couple of marks, that's what I'm going to do. So you can take any particular concentration. So if I start at 0.010 and I go down to 0.005, we've established by taking a line from 0.05 on the curve down to the x-axis that it takes 200 seconds. Now what we've got to do is go from 0.05 down to 0.0025. So what we're doing is we're dropping the concentration by half again. So I've marked on the graph that my half-life has remained constant throughout. So that proves that it's first order with respect to bromine. So by writing that on there as well as annotating the graph, I've sort of stamped my authority on it. I've said definitely that is why it's first order, and therefore there's no reason at all that the examiner has now to not give me that mark. So let's now go to the next question. So this one is about lactic acid, and it gives you 2 functional groups in the structure. And it tells you it reacts with bases and many metals. So an aqueous solution containing 1.125 grams of lactic acid is reacted with an excess of magnesium, producing hydrogen gas. The excess magnesium is removed and the water is evaporated, leaving a white solid A. So the type of reaction with bases is going to be an acid-base reaction, commonly called neutralization, and the reaction with metals is redox. And a clue that you can always use to spot a redox reaction is there's an uncombined element in there somewhere. So if there's a metal named as just a metal as opposed to a metal compound, you can take it to mean it's got an oxidation state of 0, so it's an uncombined element. So the next part of the question asks you to calculate the volume of H2 gas produced, measured at room temperature and pressure. So to do this, we've got to just have the structure there so we can work out the MR, first of all, how many moles we've got. The first thing to do is to calculate the MR like I just mentioned, which is 90 grams per mole. To get the number of moles of lactic acid, you have to do mass over MR. Moving the screen down a little bit, that gives us 0.0125 moles. So looking at the equation reacting magnesium with lactic acid, I've changed my lactic acid into the structural form instead of the molecular form. You can see that there's 2 moles of lactic acid react with 1 mole of magnesium, because magnesium is a 2+ ion when it turns into an ion, because it's group 2, so therefore it will react with 2 lactic acids, because lactic acid only has 1 acidic hydrogen. So the moles of hydrogen gas will be the moles of lactic acid divided by 2, because it's a 2-to-1 ratio in the equation that you can see. So therefore the volume is going to be that number of moles times 24,000. I've given the answer in centimetres cubed or decimeters cubed. Provided you get the right number with the right unit, you'll be fine. So shifting the page down a bit, it says, what is the empirical formula of the white solid A? So remembering that 2 lactic acids reacted with 1 magnesium, we can work it out to be C6H12O6 Mg. So this question is quite open-ended, isn't it? It says, predict 2 reactions of lactic acid, each involving a different functional group. And it says, do not include a reaction with bases or metals. So for each reaction, state the type of reaction, reagents and conditions, and draw the structure of any organic products formed. So to answer this, I'm going to do a little flow diagram instead of actually do all the different possible answers you could get. So what would happen in an exam is the examiner would use their own knowledge and the mark scheme, obviously, to decide what to actually award. So if we look at the one reaction that the carboxylic acid can undergo, that isn't a reaction with a base or a metal, it's going to really be an esterification, isn't it? So I think if you look at that flowchart, that should cover the possibilities. So you don't have to do all of that, but the ones in black are the reactions that would be with the OH group, and the ones in blue are the reactions, that would be with the COOH, the esterification. So any of them would be fine. So this one talks about alpha amino acids forming anions with the general formula RCHNH2COO-. These anions can act as bidentate ligands. So this is a bit of application here. So they actually give you quite a lot of information. It says copper 2 ions can form a square planar complex with anions with the amino acid glycine, where R equals H. So let's now pause for a second and try and draw glycine out using the guidelines. So the general formula is RCHNH2COO-. So this behaves as a bidentate ligand because there's a lone pair on the oxygen and on the NH2, which I've now added in. So we've drawn the structure of the anion of glycine, but what we haven't done is drawn the skeletal formula, which is what they want for the first mark. So moving the screen down a bit, it says draw diagrams of stereoisomers B and C. And in the structures, you need to show the ligands as skeletal formulae. So for this diagram to work, you must draw copper in that form, with 4 bonds coming off it, to show the square planar arrangement. So that shows the copper in square planar arrangement with the bidentate ligand bonding in 2 different places. So there's 2 points at which a coordinate bond can take place. So just to show the 2 places where coordinate bonding takes place again, because it's bidentate, that's how the actual the complex would look. So I'm going to get rid of the sort of highlighting of the N and the O and the explanation as to how the copper must be drawn, because you need room to put the other version, because there's 2 stereoisomers, isn't there? So because it's obviously cis-trans stereoisomerism, which can be spotted by looking at the angles between the similar parts of the ligand, so for example taking the H2N, you can see it quite clearly. Obviously this isn't asked for in the question at the moment, I'm just taking it as an opportunity to explain how you can tell it's cis-trans. Okay, so the next part of the question, going down a little bit, it says anion ligands of the amino acid alanine, where R is CH3 this time, would be expected to form more than 2 square planar stereoisomers with copper 2 ions. So what we've got to do to visualize the explanation we need is to draw out alanine. So if you look closely at alanine, you can see it's got a chiral carbon, which means that you'd have cis-trans isomers as well as optic isomers. Therefore, more than 2 square planar isomers with copper 2 ions would take place. So moving on to the next part of the question. So it says here methanoic acid is added to water and an acid-base equilibrium is set up containing 2 acid-base pairs. And it asks us, you suggest the forward reaction, the mechanism for the forward reaction in this equilibrium. And your mechanism needs to use displayed formula and curly arrows and show all species present at equilibrium. So let's start by drawing out the equilibrium in structural form first, and then we can deduce what to do with the mechanism afterwards. So I've drawn out the equilibrium, but I've also put in the conjugate acid-base pairs, because although it's not asking you to do the conjugate acid-base pairings, it'll help you work out where new bonds with protons form. So let's now draw out the displayed formula of everything and work out what's going to happen. So in our methanoic acid, the H plus must be lost, so for that to happen, the bond needs to break. And for that to happen in itself, you must have had an attack by something. So the species that has a lone pair that can accept that proton would be the H2O. So that lone pair is donated to the proton, which breaks the OH bond, which gives us the methanoate ion and the hydronium ion. And just to reconnect the idea back to the conjugate acid-base pairings, it allows us to see that base 2 is a proton acceptor. So the water acts as a proton acceptor. It doesn't matter that it's actually behaving as a nucleophile as well. In this particular context, it's a proton acceptor. So let's now go on to the next part of the question. So it gives you some information about a monobasic organic acid, D. So monobasic means it only has one hydrogen ion released when it dissociates. So D reacts by both electrophilic substitution and electrophilic addition. So those two things tell you that there's two functional groups there. There's a benzene ring, and then there's somewhere else a carbon-carbon double bond in an alkene format. Then it says the mass spectrum of D has a molecular ion peak at Mz equals 148, which obviously means that the Mr of D is 148 grams per mole. Now, the carbon-13 Nmr spectrum contains 7 peaks, which means 7 environments. And the only other piece of information I didn't talk about was the fact the molecular formula of D is CXHYO2, which means that there's one H plus ion released, which must come from COOH. So that must mean that there's only one COOH group. So I'm just trialling out a possible product here. I'm taking my benzene ring and my carbon-carbon double bond, which is an alkene carbon-carbon double bond, and I'm putting them together. I also need a COOH group. So now what I need to do is check, does that structure fulfill all of the different criteria? Is it monobasic? Yes. Does it undergo electrophilic substitution? Yes. Does it undergo electrophilic addition? Yes. Does it have one COOH group? Yes. Is its Mr 148 grams per mole? Let's have a look. So far we've got all these different things that have been ticked off. We now need to check, does that structure have 7 carbon environments? So by numbering them, you can now confirm that it does. So we've ticked off our 5 points. Let's go on to the next part of the question, which, as it happens, is the next question, the final question. So it introduces a new compound called hydroxylamine. This is a strong reducing agent. And then it applies it to a common reduction. So with the knowledge that Fe3+ is reduced to Fe2+, our students suggest 3 possible equations for what actually happens. And they're planning to carry out an investigation to determine which equation is correct. So it's an interesting question, this, because it gets you to think about what exactly those equations say is going to happen. So let's look at the outline. Using a pipette, add 25 centimetre cubed of 4.32 times 10 to the minus 2 moles per decimetre minus 3 of hydroxylamine to a conical flask. Adding 10 centimetre cubed of 1 mole H2SO4 to the conical flask, followed by an excess of a solution containing 0.0400 moles per decimetre of Fe3+. Boil the mixture for 5 minutes and allow to cool. Titrate the cooled mixture with 2 times 10 to the minus 2 mole decimetre of minus 3 KMnO4. So let's just have a look at those stages and see which type of reaction each stage is undergoing. So stages 1 and 2 are to reduce your Fe3+ to Fe2+, and the redox titration in the final stage is to determine the number of moles of Fe2+ that you've got. So if you're trying to use this method to determine which equation is actually going to be the one that works, you've got to have enough hydroxylamine to support the reaction, the proposed reaction, that has the biggest number of moles of Fe3+. So if you want an excess, you need to go for equation 3, because there's 3 moles of Fe3+ to 1 mole of NH2OH. So when you're 25 centimetres cubed of 4.32 times 10 to the minus 2 mole per decimetre minus 3 of hydroxylamine, you have 1.08 times 10 to the minus 3 moles. So the volume is going to be moles over concentration, but not forgetting that concentration is moles per decimeter to the minus 3. That gives us 0.081 decimeters cubed, which is 81 centimeters cubed, which I've now put into the answer space. So the next thing that happens is the student titrates 21.6 centimeters cubed of KMnO4 to reach the end point. Now, remembering obviously that it's the 1 to 5 ratio, isn't it, between MnO4 minus and Fe2 plus. So getting the moles of everything, we have the moles of KMnO4 minus, 4.32 times 10 to the minus 4, multiplying that by 5 to get the number of moles of Fe2 plus reacted, gives you 2.16 times 10 to the minus 3 moles. So we want the ratio of hydroxylamine to iron 2 plus. So seeing as that's an exact 2 to 1 ratio, it's equation number 2 is correct. So moving the page down to the last part. The student intends to repeat the procedure to check the results. There's not sufficient time for them to repeat all 3 stages, and the student decides to omit stage 2, the boiling stage. Unfortunately, what this means is the resulting titer is much less than the original titer, so they reject the results from the repeated procedure. Now we have to think about what the reason the boiling actually in stage 2 actually is for. Now, like any reaction that's endothermic or that needs a little bit of a push to overcome the activation energy, boiling will ensure that the reaction runs to completion. If it hasn't run to completion because you haven't boiled it, it means there's less Fe2 plus available. So if there's less Fe2 plus available to react with the potassium manganate in stage 3, the titer will be smaller than the original titer that the student got. Now the last bit of the paper says the main reason for the insufficient time is the need to boil and cool the mixture for each titration. Now they want you to think about how the procedure could be modified so that stage 2 does not need to be carried out repeatedly. And they want you to give your reasoning as well. So I've just brought a copy of the original question onto the screen and used a nice little arrow there to highlight the bit we're talking about. So, in the first stage, it's quite specific about the amounts that you're using. So, if you're boiling the mixture to ensure that the reaction goes to completion, and that's the part that's time consuming because you're boiling and allowing it to cool. The idea is that you have to boil it and allow it to cool to get the reaction to go to completion. So you can't ditch stage 2, but it does say how could it be modified so that stage 2 does not need to be carried out repeatedly. So if you used larger quantities of reagents in stage 1, you'd be able to do several titrations, and that would mean that several titers could be separately boiled, and you wouldn't have to do repeated stage 2s. You could do all of the stage 2s at once and have them separately laid out but being boiled and then cooled. So that saves some time. Okay, so that's the end of this walkthrough. Hopefully it's been reasonably useful for you and gives you an idea of the kind of flexible thinking that you'll need to get used to be able to succeed in the synoptic paper in the summer. So try and take away some of the stuff we've been mentioning, some of the tips, some of the things to maybe go and recall. If you need to go and do some flashcard work and some recall work, then so be it. But all the best in your exams, and thanks for listening. See you soon.